Let's wait couple of minutes, then we will start. Let others also join, and we can start.
Yeah, sure.
My screen is visible.
Yes, it is visible.
Okay, thank you. we can start and people can join later also. So let me start the session again by introducing myself, because some people may be watching this video later, because I'm recording the session. I am Ananya. I'm a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. In today's session, this is the week 5 for the course Semiconductor Device Modeling and Simulation. Today I will discuss some of the problems, numericals related to BZT and metal semiconductor junctions or Schottky barrier diode. Those were covered in the session. So this is the first question, question 1. A BZT is in common base configuration and it is used to amplify a signal received by a 50 ohm antenna. So there should be 50 ohm. Okay, assume KT by Q is 25 millivolt. The value of the collector bias current in milliampere required to match the input impedance of the amplifier to the impedance of the antenna. So what is the value of collector bias current? So that is IC, and the unit is in milliampere. So all these options have unit in milliampere. So let's go through this question step by step. First, let me check. Just give me a minute. It's okay, let's go through the solution. So first it is given that it is in common base configuration. So where is my cursor? So before going through this solution, let me give some of the parameters. Those are used in small signal model of BZT. So few. Small signal model parameters. First one is the transconductance. which is denoted by Zm, and the expression for transconductance is delta IC, change in the collector current, divided by delta VBE. So that is the input voltage. So this we can write as DIC in small signal model by dVBE. Okay. Which is given as IC by VT. If you use the expressions for IC, then we get the final answer as this IC by VT. So what is VT? VT is the thermal voltage. Another parameter, that is emitter resistance. Which is denoted by a symbol small re, and it is Vt by IE. Okay, so this is like the resistance of a diode, because a transistor, NPN transistor is, or PNP transistor is basically like two diodes. So this expression is, and this expression might be familiar to you because this comes in the resistance of diode also. Okay, so using these two small signal model parameters, we can write Gm into Gm into IE is alpha. Okay, what is alpha? Alpha is IC by IE. Okay. Now RE is Vt by IC. We can write this is because, let's consider alpha, which is IC by IE, that is approximately equal to 1 unity. So this is an assumption we often make to do calculations, because we want in our transistors the base current should be as low as possible, and we want a high collector current. Okay, and so that we get the amplification. So this is a reasonable assumption. Emitter resistance is equal to Vt by IC. So if someone joins later, I can show you the question again. Okay, so here BZT is in common base configuration, and we need to calculate the collector bias current, that is IC, to match the input impedance of the amplifier to the impedance of the antenna. So what is the impedance of the antenna? That is 50 ohm. Okay, you can consider it is just like a 50 ohm resistor connected at the input side. Okay. Now we get the emitter resistance, and for this circuit, that will be the impedance. Okay, if we look for, from the input side, and to match the impedance, which is the that is the 50 ohm antenna, this impedance should be equal to 50 ohm. This comes from the small signal model of BCD. Okay, so 50 ohm is equal to Vt is given as 25 millivolt. Okay, that is the thermal voltage. So 25 millivolt by IC. Let's not write it as 25 into 10 to the power minus 3 because we want IC in as milliampere. Okay, so what will be IC? (25 millivolt by 50). So this is 1 by 2, so 0.5 milliampere. Okay. Which is the collector current. Okay. So the answer is B, 0.5 milliampere. I hope this question is clear. See, there are people at the next, let me give you a theoretical question. You can try. Let me write the question first. So consider the two statements. S1 and S2. Okay. Let me write the statements. S1, the beta of A Okay, so this is the first statement. The beta of a bipolar transistor reduces if the base width is increased. Okay, what is beta? Beta is the current gain, so which is given by IC by IB, collector current by base current. And statement 2 is the beta of the bipolar transistor increases if the doping concentration is increased. So here by doping concentration, I mean the doping concentration in the base. Okay. So these are the two statements. So which one of the following options is correct? So I'm giving you four options. So both S1 and S2 are true. Both the statements are true. Or S1 is false and S2 is true. Or S1 is true and S2 is false. Or both S1 and S2 are false. Okay. You can think about it and tell me the answer. So what happens to the current gain, that is beta? So beta is uh, common emitter current gain of BCT. So how beta is affected based on the base width and the doping concentration. So what the effect? Okay, let's go through the answer. We want to determine we want to know the relation between beta and the device parameters. What are the device parameters? The dimensions of all the regions, and then the doping concentration. So these are mainly the device parameters. Other parameters like diffusion length and diffusion coefficient, those are more or less constant. So we have more control over the parameters like doping concentration and the device dimensions. So we will discuss the effects in terms of those. Okay. So it was discussed in the lectures videos. So what is the expression for beta? It is, let me write the expression first, cos hyperbolic W by LP. Okay. So here what is W? W is the effective base width. Suppose it is a PNP transistor. As we discussed earlier, if this is the emitter side, so it is heavily doped. This is base and this is collector. Okay. The doping concentrations are Ne much greater than Nb, which is greater than Nc. Okay. And because if Ne is much greater than Nb, so the depletion region here will be very less. We can neglect that. So this will be the depletion region in this junction, P plus N junction, and the depletion region will be like this. The depletion region will be more in the collector side because the doping concentration is less. Okay. This is the dimension. This is the width of the base. Suppose XB, but the effective base width is this W. So here dE, which is the diffusion coefficient in the emitter region, and if it is a PNP transistor, what will be the diffusion coefficient, that is dE. So that is for electrons, because electrons will diffuse from this base side to emitter side. So this is dNe. Similarly, dB is dPB. Okay, holes from this emitter side will move to this base side and that will diffuse. So that is why the diffusion coefficient for hole is used here. LB and LE, these are diffusion length. Okay. Here LB will be diffusion length for the holes and LE will be diffusion length of the electrons. Okay. Here NB, so it is the doping concentration in the base region. And Ne is the doping concentration in emitter. Okay, so from this expression what we can write, to have high gain, that is beta, we need NB much less than Ne. Okay, so that is how this condition for fabrication of the actual VZTs are coming from. Okay, so NB much less than Ne. So now what will be the effect of base width on beta, that is current gain? So in the question we want to know what is the effect of base width in beta and what is the doping effect of doping concentration in beta. Okay, so when base width, let me write it here. When base width increases, so overall the effective base width also increases. Then there will be more recombination of the carriers. Those are diffusing from emitter side to base side, and that will eventually decrease the collector current. So that will decrease the current gain of the transistor. Okay. So here the majority carriers are holes. So holes diffuse to the base side, and the concentration of the diffused hole will decrease. No, it might decrease exponentially or linearly based on the dimensions. So it will decrease because some of the holes will recombine with the electrons in the base region. Okay, and if the width of the base region is more, so there will be more recombination, so all the holes will not reach to the collector side, so that will eventually decrease the collector current. Okay, it's just some message. Okay, it's fine. Also, if doping in the base is increased, then also recombination increases in the base region. Then also beta decreases. So all this information we can get from this expression of beta. So if W increases, beta will decrease, and if the doping in the base region increases, then also beta will decrease. Now, how we increase current gain? Ideally, we want a high current gain. So, to understand that, let's consider an NPN transistor. This is emitter, base and collector. This is N plus Pn. Let's consider it in the forward active region when we use it as amplifier. So forward active region is what? Emitter base junction is forward bias. Okay, just connect it to negative. And collector base junction is reverse bias. This is emitter, base and collector. Let's consider it like that. And because it is n plus, so electrons will move from this side, from this emitter side, and then will cross the base and then reach collector. Okay? And holes will move in this direction, in this n plus p junction. Now we want high electron current because those electrons actually reach the collector, and so that gives us the collector current. Okay, so in the emitter base junction, total current is In plus Ip, so electron current and hole current. And so from the diode current equation we know that I equal to I naught, that is reverse saturation current, exponential QE by KT minus 1. Okay, and I naught is, so obviously the current depends on the applied voltage, but what is this I naught part? So that is Q in dP by En naught, minority carriers, plus dN, and it is multiplied by cross section area of the junction. Again it is equal to Q dP by LB. Pn naught we can write as Ni square by Nd plus Dn by Ln Ni square by Ne multiplied by the cross section area. So this gives the hole current and this part gives the electron current. Okay, now we want a high electron current, so to increase In, what we need to do, decrease the doping concentration in the P region. Okay, decrease the doping concentration in the P region. So without going through this expressions for BGT also, we can directly say from the diode current equation, if we want a high collector current, we want this in case of PNP transistor, we want this electron current component should be high, and for that we want a low doping concentration in the base region. Okay, so what is the answer for this? Here the beta of a bipolar transistor reduces if the base width is increased, so that is true because of the recombination, and the beta of the bipolar transistor increases if the doping concentration is increased, so that is not true. Okay, so the answer is C, which is S1 is true and S2 is false. I hope there are people in the meeting. Okay, let's go through the third question. So in a transistor having finite beta, forward bias across the base emitter junction is kept constant, so VBE is constant, and the reverse bias across the collector base junction is increased. Okay, so the BZT is in forward active region of operation because the base emitter junction is forward bias and the collector base junction is reverse bias. So VCB, so this is the reverse bias voltage and this is increased. Okay. Neglecting the leakage across the collector base junction, so we are not considering the leakage current, and so that is the ICBO part. And at the base also, what will be the effect of current, how the current will vary in the device, okay, whether it remains constant, increase or decrease. Let me go through this. So let's consider a PNP transistor. Emitter is highly doped, so P plus N and P. Let's consider a depletion region in this junction only in the base side. This is the depletion region. So this is emitter, base and collector. Okay. So this is the effective base width for a particular reverse bias of collector base junction. Okay. Use another color. And suppose this is the depletion region for another collector voltage. Okay, so suppose this is WB1 effective base width for a particular voltage, and this is WB2. Okay. So what will be the relation of collector base reverse bias voltage? So CB1, that will give a effective base width at WB1, and CB2 gives a effective base width of WB2, and CB2 is more than VCB1. Okay, I'm using this modular sign because I'm not worried about the convention here, whether I should write CB or BC. It can be anything based on whether it is a PNP transistor or NPN transistor. Okay, if the magnitude of the reverse bias voltage is more, then the depletion width will be more and WB will be less. That is, the effective base width will be less. Okay, and VEB is constant as mentioned. Now emitter current, let's take it almost equal to QA dB by WB B0 exponential AKT. So we are only considering the whole current part. Okay, the holes, those are traveling from this emitter side to base side. So because of the doping concentration, as we discussed earlier, this component, the whole current component, will be significant compared to electron current component for PNP transistor. Okay, now here you can see that as effective base width decreases, current increases, right? So what it implies, that if the reverse bias voltage is more, then the effective base width will be less. Okay, and then the emitter current will actually increase. That means collector current also increases. Okay, and we know what is the current gain formula. So if you remember the expression for beta and expression for alpha and alpha t base transport factor and all the current gains, then you can use the expressions also directly to get this answer, but I'm just giving you a qualitative picture here. Okay, so what is the expression for beta? Beta is okay. So if you remember the expression for beta, so you can directly say that as WB decreases, then current gain beta will increase, so IC also increases. And IC is approximately equal to IE. Okay. So let me write down the conclusion here from the discussion. So when the effective base weight decreases, the recombination in the base region also decreases. So IC will increase. Okay. Okay, in case this meeting does does not work after 1 hour, then use this link. I have already given in the chat box. You can maybe copy and paste somewhere. Uh, Use it only if this meeting does not work. Okay. Okay. This is a numerical. Next, go to the next question. So in a PNP transistor, emitter doping is 5 into 10 to the power 18 per centimeter cube. Base doping is 10 to the power 17 per centimeter cube, and a base width is 0.985 micrometer. Okay, so you can see the emitter doping is much more than base doping. And what are the typical values that you can get from this question? And the base width is 0.985 micrometer. Okay, the diffusion lengths for electrons and holes are same, and which is 10 micrometer. Okay, and tau n and tau p is those are given, which is 10 to the power minus 7 second. Find the emitter injection efficiency. So what is emitter injection efficiency? It is gamma. Okay. So what is gamma? And base transport factor alpha T, and the transistor gains alpha and beta. So what will be the values for these parameters? Okay, and the electron and hole mobilities are given 1250 and 450 centimeter square per whole second. Okay, electron mobility is generally higher, so that is why it is 1250, and then hole mobility is given as 450 centimeter square per whole second. Okay, let's go through this question. So it is a PNP transistor. And parameters, those are given Ne. Okay, doping concentration, the emitter. So it is a PNP transistor, so that this is also we can write as NaE. Five into 10 to the power 18 centimeter per centimeter cube. NB, B is doping concentration. This will be NDB, which is 10 to the power 17 per centimeter cube. Okay. Base width, so let's consider it like it is almost equal to effective base width, so which is 0.985 to 10 to the power minus 4 centimeter. So I'm writing everything in terms of centimeter because then the calculations will be easy. Okay. And the diffusion lengths are given. So diffusion lengths are denoted as Ln and Lp. It is 10 micrometer. Again I am writing in terms of centimeter. Okay. Tau n and tau p, recombination lifetime for electrons and holes, those are given as 10 to the power minus 7 second. Okay. Mu n, electron mobility is given as 1250 centimeter square per volt second, and mu p, these are given as, this is given as 450 centimeter square volt second. Now first we want to calculate what is the emitter injection efficiency. So I'm directly using the formula for emitter injection efficiency. So these formulas were derived in the lectures. You can refer to those. So gamma is given as 1 plus this whole thing inverse. Now we have all the other parameters here, but we don't have dE and dB. So for that we will use Einstein relation, which is diffusion coefficient by mobility is equal to kT by Q. Okay, mobilities are given, so we can get the diffusion coefficient as kT by q into mu. Okay, so this expression is valid both for electron and hole mobilities. So using this expression, and let me simplify a little bit here. Lb and Le, so the diffusion lengths, those are same for electrons and holes. So it is a PNP transistor. So one diffusion length will be electron diffusion length and hole diffusion. So it is a PNP transistors. So holes will diffuse to the n side. So Lb is actually Lp, and electrons will diffuse this side, emitter side. So that will be Le will be Ln, okay, electron diffusion length, but those are equal, so we can cancel each other, and dE by dB, so that will be mu E by mu B. So in the emitter side, so in the emitter side, holes are diffusion, right? Okay, in emitter side the electrons are diffusing, so this is mu n. This is mu n, okay, of the p side. Let me write p plus side, so that is in emitter side, which is divided by mu b. So in the base side, holes are diffusing, so this will be the hole mobility of the n side, okay, mu b. Nb by Ne, this we can write as 10 hyperbolic W by L. Let's consider the effective base width is approximately equal to the total base width. Okay. Now we have to simply put the values and calculate. So 10 hyperbolic of x is exponential x minus exponential minus x by exponential x plus exponential minus x. Okay. So exponential of 0.0985, that will be 1.103. Okay, exponential of minus 0.0985, that will be 0.906. So 10 hyperbolic x is 0.906. 0.098. Okay. So we can put this value here 0.098 and can calculate. Point 9946 approximately. Okay. Now this is the emitter injection efficiency. Next term is the base transport factor. Which is ICP by IEP. And the formula is 1 by cos hyperbolic W by L LB. Again we can use the expression for cos hyperbolic, which is okay. We have already calculated exponential of W by LB. So what will be alpha T? Point 9955. Let me see if those are in question. Okay. Okay, so here it is 52. So maybe if we use the exact values, but yeah, 995. Okay, let's calculate the other two values, alpha and beta. Alpha is given as alpha T into gamma. So what will be the value here? Okay. And beta is alpha by 1 minus alpha. So that will be approximately equal to 96. So what will be the answer? Think point answers. Okay, so the answer is C. So let's go to the next question. Question 5. A silicon PNP BZT has the following parameters at room temperature. So room temperature means Kt by Q is 26 millivolt. Okay. So for emitter, the doping concentration, the mobilities and recombination time, those are given. Similarly for base and collector also. And the base width is given 0.2 micrometer, and area of cross section is 10 to the power minus 4 centimeter square. So everything is given in terms of centimeter, and Kt is 0.026 electron volt. So that I already have written. Okay. If intrinsic carrier concentration Ni is 1.5 into 10 to the power 10 per centimeter cube, so which is the intrinsic carrier concentration in silicon at room temperature, calculate the charge stored in the base when VCV is 0 and VEB is 0.7 volt. So the emitter base junction is forward bias, you can see. Here you can observe that mu1 and mu p, these are less compared to mu1 and mu p in base and collector, because these values depends on the doping concentration also. I think I have mentioned this in one of the sessions. Okay. So what we want to calculate, what is the charge stored in the base region, okay, for this bias conditions. Give me a minute, please. Okay, let's solve this question. So it is a PNP transistor. Okay, let me first draw that. So it's to be P plus. Okay, this is emitter, base, collector. Okay, so emitter terminal is connected to 0.7 volt. Okay. So here this junction, P plus N junction, is forward biased. Okay, and so these two are in the same potential. Okay, now because It is given as Ne is much greater than Nb. We can neglect the depletion region in the emitter side and let's consider it only at the base side. Okay, holes will diffuse in this direction, electrons in this direction. Okay, and there will be a depletion region here. Okay. Now let me draw the excess carriers in the base region. Okay, so this is the base region. Let's consider this direction as x-axis. And the holes which are injected from the emitter, that will those holes will have a distribution like this, the excess holes in the base region. Let's consider this is P1 and this is P2. So what that is P1 and P2, these are excess hole concentration and this is the effective base width WB. Excess minority carrier, so if this point is x equal to 0, then P1 is almost equal to okay. How we can determine the excess minority carriers in at the junction edge or the depletion region edge? So this kind of equation that you have already observed in the derivation of diode current. So the excess carrier depends exponentially on the applied voltage, and it also depends on the already those which are minority carriers, those are present in the base region. Okay, similarly P2, that will be Pn0 Cb, which is 0. Okay, and the distribution for excess minority carriers is like this line. It is a linear the distribution is linear because we are considering the base width is, so the base width the effective base width, this is much smaller than the diffusion length of the holes. Okay. Fusion length of the holes in the base region. I am writing LB because this will be valid for NPN transistor also. Okay, that is why it is a linear distribution, not an exponential decay. And what is Pn0? It is Ni square by Nb. Okay. Now it was the question. The question was that calculate the charge stored in the base region. Okay. So these are the excess charges which are stored in the base region. So let's consider QP as the total charge in the base. Now how we can calculate the charge in the base? So it is like a triangle, so we can use half. This is WB P1, and we have to calculate the cross section area like this direction. Okay, so multiplied with area, and we multiplied with Q because of the charge. Okay, so this is the expression for the charge in the base region. Now let me simplify this. Half Q A WB Ni square by Nb exponential of, so which what is VEB 0.7, and it is given as room temperature. Okay, it is given as room temperature, and KT is 26 milli electron volt, so VT will be 26 millivolt. Okay, so this is 0.026. What are the values? Q is 1.6 into 10 to the power minus 19. Area is given as what is given as area? 10 to the power minus 4 centimeter square. WB is given as 0.2 micrometer. Okay. 0.2 into 10 to the power minus 4. Let's write in terms of centimeter. Ni is 1.5 into 10 to the power 10 square. Nb is 10 to the power 16. And then the exponential term. Okay. Let's check the unit. So it is charge, so coulomb. Area is centimeter square. WB is centimeter width, so this is centimeter. Ni square is per centimeter square per centimeter cube whole square, and Nb is also per centimeter cube. So this will be per centimeter cube. Okay, and this term is unitless. So what we have is coulomb, so which is the unit for charge. Okay, so what will be the answer here? QB missed a few terms here. Okay, so answer I'm getting is approximately is 1.8 into 10 to the power minus 12 coulomb. Okay, you can check the calculation. There might be some error because the answer is given as 1.97 is 10 to the power minus 12. So the correct answer is C. Might have done some mistake in the calculation, but the order is correct. So that is 10 to the power minus 12 coulomb. Okay, but the process to calculate the charge stored in the base region is this. Okay, so let's go to the next question. This is question 6. It is a silicon PNP transistor. It has the parameters. It was similar the way those are given in the last question. Okay, the base within the area of cross section is also same, and KT is 0.026 electron volt. That means the transistor is in room temperature. Okay, if the base transit time is the dominant delay component for this BZT, what is the FT? Okay, what is the frequency of operation for the BZTs? Okay. So in a transistor, in a BZT, it involves certain delay component, that is because of the charging and discharging, the movement of the carriers. Okay, and based on that, up to which frequency we can operate these transistors, those are determined. Okay, here for this question it was given as the base transit time, that is the dominant delay part. So it is a PNP transistors, holes will move here and it will travel the base region, and then the electric field here will actually capture the holes, and then that will give rise to the collector current. Okay. And the time it takes to cross this base region, the neutral base region, that is the dominant delay for this BZT, for this design. Okay, so what will be the delay? Okay, and based on that, what will be the frequency of operation, the maximum frequency of operation we can get for this BZT, that we need to calculate. Okay. So let's go through this question. So first let's calculate the base transit time. the time it is required for the carriers or the charge to move the neutral base region. Okay, it is the PNP transistor. This is the neutral base region. This is excess holes here, excess holes here. This is the effective base width. Okay, and let's consider the BZTs in forward dielectric region. Okay, so there will be some uh, minority carriers or excess carrier in the base region. So based on the type of the transistor, it will be QN or QP. So what is QN or QP? These are the minority carrier charge in the base region. Okay, here, so holes will be injected to the base region. So the minority carriers in the base region, that will be QP. Okay, and we calculated in the last question. So what will be QP? That is half Q A WB P1. Now the holes will diffuse here in the base region, and then the holes will be collected by the collector. So that is why the name collector. Okay, so the whole collector current will depend on the holes here and the distribution of holes. Okay, okay. Why collector current depends on the slope of the holes? Because the holes will diffuse as the concentration gradient is like this. So holes will diffuse and it will give collector current. Okay, and the expression for collector current, we are using a simplified expression. We are not considering the reverse bias current here. Okay, so that will be Q A, diffusion current basically, dP P1 by WB. Here P2 is, we are considering as 0. This point is x equal to 0 and this point is x equal to WB. Okay, so the concentration, from the concentration gradient we are getting this P1 by WB term. If you look at the expression, it is the diffusion current of holes. Okay, now this is the charge in the base region and this is the collector current. Okay, how we get collector current? So that is basically IC is equal to charge by time, so current equal to q by t, right? So qp by some time t. So what is this t in our case? So that is the base transit time. Okay. So what is base transit time? Tau is qp by ic. So qp is this expression, qa, those terms will be cancelled, p1 will be cancelled, so that will be wb by 2 wb square actually, yeah, 2 dp. Okay, now what is wb? So that is given in the question, 0.2 micrometer, and dp, so we don't have the dp information, but we have mu n and mu p in the base region, so we'll use these. So mu p is 400 centimeter square per volt second. So let's use that first. So from Einstein equation, dp by mu p is equal to kt by q. Okay, so dp is equal to kt by q is given as it is a room temperature, so that is 26 volt because it is divided by q. Okay, then mu p is given as 400. Okay, so that will be 10.4. And what will be the unit? So this is volt, and what is the unit for mu p? That is centimeter square per volt second. So the unit will be centimeters square per second. Okay, that is the unit for diffusion coefficient. Now let's put it here and calculate. 0.2 micrometer, so I'm writing in terms of centimeter. So this is centimeter square, this is centimeter square per second, so the final unit will be in second, which is the unit for time. So what will be the value here? Tau (1.92 into 10 to the power minus 11 second). So okay, we have to calculate finally the ft. Yeah, ft in hertz. So we have already calculated the base transit time. So this is the dominant delay in the BZT. So what is ft? So the ft actually known as unity gain frequency. Okay. So it is the frequency at which common emitter current gain. So what is common emitter current gain? That is beta becomes unity. Okay, and how we calculate frequency? So this like the general formula here, 1 by 2 pi tau. Okay, so tau here, so there may be various delays, but the dominant delay is the base transit time, so we'll use that, and we'll calculate the frequency to so that will be 8.29 to 10 to the power 9 hertz. So that is approximately equal to 8 gigahertz. So this BZT with these parameters can be used up to 8 gigahertz reliably. So okay, after that the gain decreases. Okay, so the answer is C. Hertz. I hope this question is clear. Next, this is again a similar question. Find Ft for an NPN transistor with base transit time tau t as 100 picosecond, and the collector capacitance and the resistance of the collector region is given in the depletion region, and the emitter junction charge is in 20 picosecond, and the electron drifted saturation velocity, which the saturation velocity is 10 to the power 7 centimeter per second through the 1 micrometer depletion region. Okay, so here it is not given as the base transit time is the dominant delay time, so we have to consider all the delays in the collector depletion region and the emitter depletion region, and the time it takes to generate a carrier and transfer of the carriers. Okay, we will basically add all the delays, and then we will calculate the unity gain frequency. So if let's calculate the total delay first, and then you can see that the base transit time is indeed the dominant delay time in most cases. So total delay time tau d, first is the 100 picosecond plus this is 30 picosecond, let's add this, plus so saturation velocity is given, and the length of the depletion region is given, so the time it takes will be 1 micrometer is 10 to the power minus 4 centimeter by 10 to the power 7, so this is centimeter per second. Let's make it picosecond, okay, because all of the delays are in terms of picosecond, so 10 to the power 12 plus in the collector region what will be tau we generally get how we get tau multiplied by resistance and capacitance, so tau is R into C, so using this formula, so multiplying 0.1 picofarad into 10 ohm, okay, that will give us the delay here. So this will be 100 plus 30 plus so 7, okay, 10 plus first one. You can see here the base transit time, and that is the significant delay, and it will be 141 picosecond. Now we can calculate ft, unity gain frequency, as 1 by 2 pi tau t, which will be, let me calculate, 1.1213 actually. To the power 9 hertz, which is 1.13 gigahertz. Okay, so the answer is A. Okay, I have 3 more questions. Let's go through it quickly. Let me write a question here. NPN transistor is operating in the active region, that means forward active region. If the reverse bias voltage across the base collector junction is increased, then what will happen? Option A, okay, so the BZT is in the active region, and if the reverse bias voltage across the base collector junction is increased, what will happen to the effective base width and the common emitter current gain. So what is common emitter current gain? That is beta. So how it will be affected by reverse bias voltage. Let's go through it. So it is an NPN transistor. This is emitter, base, collector. It is in forward active region, so it is negative connected. Let's say ground. Say positive. This is VCB, which we are changing. It is in the active region, that means emitter base junction, that is in forward bias. And collector base junction is reverse bias. Okay. And we are increasing VCB. It is the magnitude of the reverse bias voltage is increased in this junction. Okay. So what will happen if WB is the effective base width? This is the total base. This is the depletion region for particular VCB, and after increasing VCB, this is the depletion width. This is the effective base width. So any kind of recombination happens, the carriers which are injected from the emitter side, that will happen in the WB region, that is the effective base width region. Okay. So with increased VCB, WB decreases, so effective base width decreases. Okay. Similar to the reverse biased PN junction, right? And what will happen to the common emitter current gain? Okay, let's see here. Okay, first, what is base transport factor? How it is affected? We know that more the carriers will be in the base region, there will be a chance of recombination. So let's first see the base transport factor, which is alpha t. It is given as 1 by cos hyperbolic W by L. Okay, for small this term, we can approximately write it as using Taylor expansion for cos hyperbolic x. It will be 1 by 1 plus half W by LB square, which again we can use 1 plus x inverse Taylor expansion for that. That will be 1 minus half W by LB square. Okay. Now to have high alpha t, W should be very very less than LB, that is the diffusion length of the carriers. So it is a PNP transistor, so that will be the diffusion length of the electrons in the base region. Okay. Now how gain is affected? We can correlate this WB of the base with the reverse bias voltage. So that is the question. Gain are alpha is equal to alpha T gamma, and beta is equal to alpha by 1 minus alpha. Okay. So as effective base width decreases with increase in the reverse bias voltage, so gain increases. Or we can say that when effective base width decreases, so there will be less chance for a combination, so overall gain will increase. So what will be the answer? Answer here is effective base width decreases and common emitter current gain increases. So the correct answer is B. Let's quickly go through two questions on Schottky barrier diode. So Schottky barrier diodes are metal semiconductor junctions basically instead of a PN junction. Okay. So the question is, the Schottky barrier diode, so it is also written as SBDs. I will use this short form. Okay. So the question is, which of the following parameter of a silicon Schottky barrier diode is higher than that of the corresponding PN junction diode? Forward voltage drop, reverse saturation current, or reverse recovery current. So which one is higher in Schottky barrier diode? Okay. So the answer is, so in case of Schottky barrier diode, it is a metal semiconductor junction. So this is the Fermi level. So let's see, it is a metal and this is an N-type semiconductor. Let's consider silicon. Okay. So this QV now, so this voltage drop, that will be equal to phi m minus phi s. Okay, what is phi m? It is the work function of metal. Um, and phi s is the semiconductor silicon work function. So the typical values for V naught in Schottky barrier diodes, what the typical values are, you can refer to any book, you will get this, because metal work function, those values are well known, and then phi s for silicon. That actually depends on the this doping concentration, but this values varies in the range 0.2 to around 0.4 volt. Okay, so this is much smaller than the PN junction diode, which is typically around 7.7 volt. Okay, so for a voltage drop, this is not higher, but the reverse saturation current is higher. Okay. In Schottky barrier diodes are higher. Then that of PN junction. Okay. This reverse saturation current depends on the this barrier height. Actually, exponentially depends on this barrier height. So that is actually higher in case of Schottky barrier diode compared to PN junction. So the answer will be B. Okay. Don't think we have much time. Yes. Okay, let's go through the last question. It's already 5, but quickly go through this last question. Schottky barrier diode is used as a the options are voltage reference, high frequency switch, tune circuits, current control attenuator. Okay. So the Schottky barrier diodes, as I mentioned, these are the metal semiconductor junction. Okay. Too low. It is metal. This is semiconductor. This is N-type semiconductor. See? And this barrier height, this another Venn diagram, those were already discussed, so I am not discussed again. This is equal to Q phi m minus, so the electron affinity of semiconductor, and this is Q phi m minus phi s, or function difference. Okay, so in case of when it is forward bias, so electrons will be, because it is an n-type semiconductor, electrons will be injected to metal, okay, from semiconductor side. Electrons here is the majority carrier, so it is a majority carrier device, while BZT is a minority carrier device, or in PN junction also. And here in case of this, the total capacitance will be less. Why total capacitance will be less? Because there is no concept of no diffusion capacitance. Now we know that capacitance is related to delay. Okay, higher the capacitance, higher will be the delay. Okay, if the delay is high, the frequency of operation will be less. Okay, so here because it is a majority carrier device and the total capacitance is less, there is no concept of diffusion capacitance like we have in case of PN junction diode. So the total delay uh, for this Pattern semiconductor junction or Schottky barrier diode will be less. That is why these are used as for high frequency applications. Okay. Only drawback is the reverse saturation current is higher, but for higher frequency applications, those are used as high frequency switches. Okay. Okay. Right. Let me stop sharing that. Okay, let's end today's session. We have discussed some numericals and concepts on BZT, and then we also discussed some of the concepts of Schottky barrier diode or metal semiconductor junction. Okay, thank you everyone. I hope the session was useful, and we will meet in the next session. Okay.
We will be getting the recording, right? On the course website.
Yes, yes. I think you are
Okay.
getting mails. I'm not sure, but
Yeah.
might have given.
Yeah. Yes. Yes. Yes.
Okay.
Ma'am, I have a doubt regarding the assignment that is being provided to us for assignment number 5.
Okay, I actually have not checked the assignment, so can
Basically, the question says, there is a question number 2 which says, find for a bipolar junction transistor using Eber-Moll model with IF naught 1.25 10 power 16 ampere, IR naught equal to 0.5 into 10 power 16, negative 16 ampere, and alpha F 0.996. What we are required to find out in this question?
okay, see the assignment questions. I'm not actually dealing with that. Maybe you can post it in the discussion forum, so maybe they will be able to help you out because these
All
questions
right,
I'm not very sure.
all right, sure.
Okay, okay. Thank you, everyone. Bye.
Yeah.
Thank you.
Thank you.